This presentation is delivered by the Stanford Center for Professional Development.
We are going to do today an interesting application of the Fourier transform. It will involve a little bit of deltas and some properties of delta, and actually it will involve a physical interpretation of delta, which I think is actually quite interesting. But it's, regardless of that, regardless of the particular ways that delta enters into it, it's interesting itself because it's a nice application of the Fourier transform. It's the kind of thing you'll see in other classes depending on the direction you go in your further work. That is, I want to talk about the Fourier transform and diffraction. Now, diffraction refers to a phenomenon of light. And diffraction refers, for our purposes, it is analyzed and understood in terms of the wave theory of light. So we're not going to get into the raging battle between the wavists and the particleists. Diffraction for us has to do with is I think pretty much I consider it like identical to interference phenomena associated with light. So diffraction is one term for it, but is pretty much equal to interference patterns that light makes passing through an aperture of light through apertures. This is not the only way that diffraction can be talked about, but that's the way we're going to talk about it, through apertures, through holes. All right? So there are a couple things that enter into this. I'll show you a picture in just a second. You have seen pictures of diffraction patterns, I'm sure, before, but I will show you a picture just so we all know what we're talking about. But I want to talk about the distinctions, what we're going to do and what we're not going to do. So it involves light from a distant source, typically from a distant source. And we'll see how that enters into it. The fact that it's distant enters into it. All right. It impinges on a plane, which is usually called the source plane, for other reasons. I'll come back to that in a second, on which a number of holes are cut. And instead of calling them holes, it sounds more scientific, you call them apertures. So you have a plane with apertures, all right, that the light passes through. The rest of the plane is opaque. Part of the plane is opaque, and then you have holes that the light passes through. And it bends around those holes, and it creates certain characteristic patterns on a plane that is some distance from this, called the image plane. So at some distance, you have an image plane. All right, and you see diffraction patterns. Now, I'll show you a picture in just a second, but right here is where I want to make a distinction between the different types of diffraction that one studies. We're going to make a number of simplifying assumptions. We're going to assume, well, first of all, we're going to do everything in the context of the wave theory of light. So for us, a light is going to be an oscillating electromagnetic wave. And really, we're only going to talk about the electric field part of it. So I am making a certain number of assumptions, but that are accurate enough to give you good and helpful understanding and good and helpful formulas. So we'll assume light is an oscillating EM field, although we're really only going to talk about the electric field. And we also assume that it's monochromatic, that there's only one frequency of light that's shining, that's being diffracted. That'll simplify writing things as well. And we're making a couple of other assumptions. The other main assumption that you make in diffraction has to do with this statement here. At some distance, you have an image plane upon which the light is incident. All right? There the distinction is between so-called near field and far field diffraction. So the distance of the image plane determines two kinds of fraction. One is called near field. which means relative to the wave, and it's usually relative to the wavelength. Let me just say it in just a second. Near field, which means it's close in, that's called Fresnel diffraction. Fresnel, I think that's right, diffraction. And the other is far field, so-called far field, which is Fraunhofer diffraction. I can only hope I'm spelling those right. All right. And usually when you talk about near field or far field, you talk about distances measured relative to the wavelength. It is far away relative to the wavelength of the light, or it is close relative to the wavelength of the light. And the other thing that comes into the size of the apertures relative to the wavelength. All right. So you measure distances near or far, typically relative to the wavelength. Distances and the size of the aperture relative to the wavelength. I'll make comments about this. We're not giving by any means an exhaustive treatment. All right, this is just an example of how the Fourier transform comes in an important and interesting application. We have a whole course actually called Fourier optics that does these things in, of course, much greater detail and goes much farther with it. But I thought you'd be interested to see this application because it's a very pretty application. It's nice to see some of the ideas come in. And you'll see them again if you go on in this. Stanford has been a leading light in light for years. And in particular, Joe Goodman, who's an emeritus professor now, was a very important figure in the theory of Fourier optics and wrote a number of very influential textbooks as well as, of course, a lot of research papers. And the course that sort of exists now in Fourier optics is based to a large extent on a lot of Joe's work. Let me show you a picture so you know what I'm talking about. You have seen diffraction patterns probably in physics classes or whatever, but the picture looks something like this if I can I show this? I'm just going to show this one shot. I think there's a picture of this also in the notes. It looks like that. Amazing. Oh, there we go. Okay. We can dim this a little bit so I actually get the full effect. Can we dim the lights? Can we? There we go. All right. All right, it's just showing up a little bit. So this is, what you're seeing is the image plane. You're seeing the pattern of the image plane. The source is some distance away. It shines through. In this case, I think it's just a square aperture, a square slit that's showing the pattern. And the thing that was remarkable about diffraction patterns that really shocked people was the bands of light and dark. That's the characteristic property. What you're really seeing there is the intensity. You're seeing the magnitude of the electric field that is representing the light. All right. Actually, that's what instruments measure. They measure the intensity or the magnitude of the electric field. And what was so surprising to people when they first started observing these diffraction patterns, it goes way back into the history of physics, is the intermixing of light and dark bands. Because how can light plus light make dark? You know, I mean, how could there be darkness when all you're doing is shining light? You know, how could that be? Surely this is not God's will. You know. And it was a subject of heated debates, and again, certainly between people who advocated the particle theory of light, people who advocated the wave theory of light. The wave theory of light initially provided a much better explanation of these diffraction patterns, and that was one of the reasons why it was in ascendancy for so long, because this was a phenomenon that was not only considered important, was important to understand, that it could be analyzed by using the wave theory of light. All right, so you have anybody, I'm just curious out there, anybody ever work with these sort of diffraction patterns? There are all sorts of reasons to do it. I mean, they use it for physical measurement of wavelength of light and things like that, or they sometimes just have experiments. Yeah, how did you?
We looked at the way the distance between the diffractions, the space, how wide the dark parts were, to calculate how thick a wafer was, to calculate how hot it was if we knew its initial temperature and thickness.
Oh, yeah? That's interesting. Anybody else? I'm just kind of curious. Even in physics labs or something like that, when you were undergraduates, where you did diffraction patterns, diffraction experiments, it's kind of cool. It really is kind of cool. Okay, all right. You can show that. You can pull up the screen. Thanks. We're done. Thank you. All right. So let me give you the setup in a little bit more detail. And again, what we're going to talk about is Fraunhofer diffraction, although the initial setup doesn't matter. You'll see exactly where this comes in. And it's a certain approximation. It shows you how you can approximate one quantity in terms of another quantity if a distance is large. You'll see. But let me give you the basic setup. So again, you have a source of light, however it's defined, or however it's determined, and it is a great distance from the aperture plane. So the aperture plane is something over here. This is the aperture plane. And these holes, it is considered to be opaque, except where there are holes. So the holes are the apertures. All right? And the fact that you consider the source very far away has the practical implication that by the time it reaches the aperture plane, it does so, it's basically a plane wave coming in. All right? And what that means is that you can assume that the aperture plane is essentially, well, not essentially, you can assume it's a so-called wavefront for the wave, which means that every point here on the plane has the same phase. All right? So the fact that the source, that's the first sort of simplifying assumption. So a distant source means practically that the aperture plane is a wavefront. That is, the light is coming in as a plane wave. All right? And again, practically what that means is that everything here is the same phase, which means you can ignore the phase. Okay? It's a wavefront. So the wave has the same phase at all points of the aperture plane. All these are realistic and reasonable assumptions. All right, I just want to spell them out, which means, for all practical purposes, you can ignore the phase. You can suppose the phases. You can suppose everything sort of starts from zero at the aperture plane. All right. And furthermore, we're going to represent the electric field. Now, this is a second sort of simplifying assumption. Well, we're going to represent the light by a time oscillating electric field. And we're going to use complex exponentials for that. So you represent the light as, say, E times, E is for the electric field for the magnitude, times e to the 2 pi I nu t. All right? So E is the strength of the field. And this is the light on the, not at the source, but the light on the aperture plane. All right? So on the plane. Aperture, my writing's getting worse. Plane as e to the 2 pi I nu t. So E is the strength of the field. All right, and nu is the frequency. So this is where the other assumption comes in, that I'm working with monochromatic light, so light of a single frequency. Frequency, so again, it's monochromatic. All these assumptions can be, to a greater or lesser extent, dropped in more careful and more thorough treatments. But we're simplifying things just to get to the main punchline, which you'll see, which is pretty interesting. And we're also going to assume that the field strength is constant on the plane. All right? So we'll assume that E, the strength of the field, is constant. So we assume E is constant, say, E naught on the aperture plane. Okay. Now, some distance away, which I can't represent too well on the blackboard, is the image plane over here. All right, so light starts from the source, hits the aperture plane, and then gets diffracted by the apertures and winds up on the image plane over here. And the question that we want to address is, what is the electric field? Just think of this in terms of electric field. What is the electric field at a point on the image plane? Okay, P. What is the electric field at a point P on the image plane? All right, light passes through the slits. It gets to P from different paths. All right? And the question is, how do they all add up? Okay, so the light gets to P. The light, that is to say the wave, i.e. the wave, gets to P along different paths because it is bent when it passes through the, or it seems to be bent when it passes through the apertures along different paths. How do they add up? How do the results add up? How does it all add up? I don't know what you put it that way. All right. Now, classically, the way to address this problem is what's called Huygens Principle. It goes way back because it goes back to Huygens. And I don't know how it was initially enunciated, but the way I'll talk about it, and again, without trying to be terribly precise here. You analyze this, you approach this via Huygens Principle. Huygens, this is a challenge. Huygens Principle, which says that every point in the aperture, every point of a wave front, all right, can be itself regarded as a new source. Okay? Each point of a wave front, and by assumption, the aperture plane is a wavefront. All right, so then you have all these little. You imagine that this is made up of a bunch of little points, and each point there on the wavefront, each point in the aperture can be each point on a wavefront. Can be regarded as a new source. All right? You see what happens as a result of that. You see what happens over on the image plane as a result of light coming from a point here regarded as a new source, and then you add them all up. You add up, that is to say you integrate all these, the effects of all these sources. Now, Huygens Principle has been criticized, and it's certainly not the modern view, but it's still applied because it produces results that are intuitive and accurate enough. It's interesting, and I am by no means an expert on this, it's interesting to really read different treatments of this, older treatments of it, more modern treatments of it, and so on, to see how Huygens Principle is fared, to see how the whole approach to the diffraction is fared, and so on. But this is the way that was sort of classically analyzed, and certainly the way we're going to do it. I'm not going to say anything more than this, but you'll see how I'm going to put it to use. Matter of fact, I think I gave a reference in the notes to a book by Melvin Schwartz called Principles of Electrodynamics or something like that. I can't remember. It's in the notes. And he actually has a very interesting treatment of all these things. He tries to take a relativistic approach right from the beginning. So it's a very mathematical book, and it tries to put things in a certain context. And he has, sort of scathing criticisms of Huygens Principle and so on, but he's not above using it occasionally. All right. So here's how we're going to apply this. So once again, so forget about the source. The source is infinitely far away. Everything now takes place between the aperture plane and the image plane. All right. So I want to introduce coordinates on the aperture plane. Matter of fact, let me just focus on one aperture. So here's, say, the origin of the aperture plane. And here is a point X on the aperture plane. And I take imagine I take a very thin slice. So this may be part of a bigger aperture. Let me do it like this. But I take a very thin slice, say of width dx. All right, now this is a sideways view of this. We're essentially going to turn this into a one-dimensional problem. If you want, you can consider the plane, the aperture plane coming out like this, and I'm going to take a aperture of dimension 1 in this direction and dimension dx in this direction. All right, so it essentially reduces this to a one-dimensional problem. That's another simplification, but they're reasonable simplifications depending on the dimensions of the actual physical problem. All right, so here's P over here. So light comes out of X, or out of this little slice, and reaches P. All right? The field here, the field at x is roughly, well, let me say the field associated with a small slice is about, well, let me write it up here. The strength of the field, in the slice of size dx at x is about E naught, the strength, times e to the 2 pi I nu t times dx. So the field strength is roughly, the field strength is constant on the plane, so it's E naught dx of it in the particular slice, and then I multiply by this time varying, so it's e to the 2 pi I nu t. Okay? All right, now, and so I'm assuming I have zero phase on the aperture plane. Okay, now what happens when it reaches the image plane? All right, there's a decrease in the magnitude of E by 1 over the distance, but that's not the main effect. All right? The main change in going from, that is the main effect really, maybe I should say, the main effect in going from x to p over a certain distance is a change in phase. All right? And what we have to, yeah?
Is the e to the pi t you have there, is that supposed to be an x or is that t for something else?
T is time because it's a time varying field.
Okay.
All right, so it's an oscillating electric field. Okay? So T is time. It's actually going to come out of that's actually not going to turn out to be an important thing, but you represent the field that way. I should have said, by the way, I'm sorry. As per usual in this case, you represent real quantities by complex exponential, so the actual electric field will be the real part of that. But as is common in this case, usually sometimes call this the analytic version of the signal, the analytic version of the field. When you represent it by a complex exponential, the actual field would be, say, the real part of that. But we're sort of used to using complex quantities. I do it without thinking about it. We're used to representing real quantities by complex quantities. All right, now, and if it reaches P from all sorts of different paths, then what you want to take into account is the phase change that is associated with the different paths. So say this is a distance r. Say it travels a distance r. All right. So what is the phase change in traveling a distance r? R from x to p. Well, how many cycles does it go through? Think in terms of, measure this in terms of wavelengths. All right, if it goes through one wavelength, then it goes through one cycle. If it goes through two wavelengths, it goes through two cycles. If it goes a distance r, the wave goes through r over lambda cycles, where lambda here is the wavelength. All right? You can, so again, wavelength. All right? Goes through one, if r is equal to lambda, that goes through one cycle. One wavelength goes through one cycle. If it goes through two wavelengths, it goes through two cycles, and so on. If it goes through half a wavelength, it goes through half a cycle. In general, if it goes through distance r, then the number of cycles it goes through is r compared to the wavelength, r over the wavelength, r over lambda. You can even work that out with formulas if you want, but that's intuitively what's going on here. Okay, so what's the phase change? So the phase change is 2 pi r over lambda. All right? And so the field, or the, I should maybe say field, let me write it down, then I'll say something about a field at P due to the field at X is, let me write it like this, dE is a little bit of change in the field. The differential of the field is E naught times e to the, it's still oscillating at the same rate. That's not changing. It's still the same frequency. So it's e to the 2 pi I nu t. I'm going to need more space here, I can tell. Is E naught e to the 2 pi I nu t. As I say, it's still monochromatic. What's happened here is the phase change. E to the minus 2 pi I r over lambda if I represent the phase change also that way as a complex exponential times dx. That's the key expression. That's the key expression. There's been a drop-off in the magnitude of the field. That's true, but that pales in effect in comparison to the change in the phase. Okay, so what is the total field? Is the integral of this expression. So it's the integral over all the apertures. This is the field at P, felt from all the different sources. So it gets the P from all different paths. E naught times e to the 2 pi I nu t, e to the minus 2 pi I r over lambda dx. So I'm integrating over the aperture plane. I'm integrating with respect to x. X is the variable that describes the location on the aperture plane. So I could just say aperture. I'm saying integrating over the aperture, so I'm really thinking about integrating over the aperture plane. But the only time you get a non-zero contribution is when, because you can regard the field as being zero other than at the apertures. All right, because other than the apertures, the plane is opaque. The aperture plane is opaque. All right, so I can pull out these constants here, and it's really this is the part that depends on x because r depends on x. All right. On x. So that's where the dependence is coming in the integration. Not here, not in the time variable. All right, so matter of fact, I can pull that out, and I can more or less ignore it in the rest of the discussion. So I can write this as E equals E naught, that's a constant, I assume that's a constant, times e to the 2 pi I nu t times the integral over the apertures of e to the minus 2 pi I r over lambda dx. All right. Now, I should also say that what you observe, what you see with your eyes or what you measure with instruments is the magnitude of E. So in particular, the time varying part of that goes away because the time varying part of that under the assumptions we had, monochromatic and so on, is just a complex exponential which has magnitude 1. All right, so you measure the magnitude of E. All right. So the quantity of interest here really is the integral, not the stuff out in front of it. Okay. Is this integral over the apertures of e to the minus 2 pi I r over lambda dx. All right, now, this is not a useful expression so far. It's too complicated. All right, here's where the approximation comes in. So this is not useful. I mean, maybe there are times when you can write it out more carefully and try to evaluate the integral, but generally, sort of as a principle, as a way to understand the phenomena, it's not so useful. That is, you need an additional assumption to make it a useful expression. And that's where this Fraunhofer approximation comes in. All right, so now we bring in the so-called Fraunhofer Approximation. All right? And here's what that means. All right? So let me again draw the picture over here. Here's the aperture plane over here. Here's X. Here's the origin of the aperture plane. Here's the image plane. Here's P. That's what we've calculated. We've calculated the field at P due to all the ways that light reaches it from all possible points on the aperture plane. Let's call this distance R naught. All right? So that's the distance from 0 to P. That's a fixed distance. Here's R. All right? And I want to be sure I write this right, get this right. Here is theta. All right? Then this distance here, I'm sorry for being careful to look at my notes carefully here, but I don't want to screw anything up. That's x sine theta. That little length in there is x sine theta. We're going to assume that R, this distance, is much greater than this distance, than x. That's the Fraunhofer approximation. That's the Fraunhofer assumption. You're going to assume that R is much greater than x. All right? By that assumption, this little bit is such that if I take R naught minus x sine theta, that's approximately R. That is, the operational effect of this assumption is that R naught minus x sine theta is approximately R for all the different values of x on the aperture. So there's actually several assumptions here. The apertures shouldn't be too big, they shouldn't be too far away, but at any rate, the distance of the image plane should be very much farther than whatever x is, wherever x is varying on the aperture plane. All right? So way far away. And under that assumption, R naught minus x sine theta is approximately, so the fixed distance from 0 to P. Remember, we're calculating the electric field just at a particular point in the image plane, at a point P in the image plane, from all the different contributions. And at that point, R naught minus x sine theta is approximately R. That's the expression we plug into the integral. So you plug this into the integral, giving the field at P. And what do you get? You get, well, I'm erasing it here, but I'll write it out in just a second. Forgetting about the constants out front, you get the integral over the apertures of e to the minus 2 pi I r over lambda, so it's 1 over lambda times, and r is approximately r naught, which is fixed, minus x sine theta. So it's r naught minus x sine theta. All right? dx. dx, right. Okay? All right. Split this up. Again, I'm forgetting about the constants out front because that's not important. It's the integral, this integral that's important. And even in this integral now, we can pull out another constant that's going to be of absolute value 1, so it won't contribute to the magnitude. So that's the integral over the apertures again of e to the minus 2 pi I r naught over lambda, so that doesn't depend on x, times e to the minus 2 pi I x sine theta, oh, excuse me, plus 2 pi I x sine theta over lambda dx. All right, I haven't done anything except plug that in. All right, now pull this out because that doesn't depend on x again, right? R naught is the fixed distance from 0 to P, and we're calculating everything. We're calculating the strength of the field at P. This is equal to integral over the apertures. Oops, I forgot to pull up a constant out. E to the minus 2 pi I r naught over lambda times the integral over the apertures of e to the plus 2 pi I x sine theta over lambda dx. Okay. All right, now. It is common in the biz to introduce another variable, an auxiliary variable that replaces sine theta by just another name. So introduce P equals sine theta over lambda. One always talks about diffraction through an angle, and the angle is theta here, but this is the variable that you introduce, sine theta over lambda, so that the integral becomes, and forget about the constant out front again. The constant out front has absolute value 1. You only measure the magnitude. You only see the magnitude, so forget about that constant. Let me just concentrate on the integral. So it becomes the integral, I say equals, becomes the integral over the apertures of e to the 2 pi I xp dx. Okay, almost there. Now, let's introduce the aperture function, so to speak. All right, so something like a of x is 1 if x is in an aperture, and 0 otherwise. Okay? You're only integrating over the apertures. That's the only place where the field is non-zero. All right? Then I could write this integral a little bit differently. I can imagine integrating over the entire aperture plane, that is to say from x going from minus infinity to infinity, of a of x times this, because a of x is only 1 when I'm in an aperture and it's 0 when I'm not in an aperture. So I can write the integral as the integral from minus infinity to infinity of e to the 2 pi I xp a of x dx. Okay? And now, what do we recognize? This is, of course, nothing other than the inverse Fourier transform of the aperture function. At p. The dual variable here, the variable in the Fourier transform, the formula for the two variables in the Fourier transform are x and p. P is sine theta over lambda, so p has to do with the geometry of the situation. But as far as writing the formula goes, if you recognize this as a Fourier transform, the variables are called x and p, and this is the inverse Fourier transform at a at p. Now, I have to make a couple of comments here, so I take a deep breath. You know, I said once that people have different conventions about what they call the Fourier transform, you know, where they put the 2 pi's and sometimes either where they put the plus and where they put the minus. Remember I said that? And, you know, different fields have different conventions. Well, in physics, it's more common to define this as the Fourier transform, and the integral with a minus sign is the inverse Fourier transform. And so if you were in physics and somebody wrote down this formula, they wouldn't write this is the inverse Fourier transform of the aperture function. They would write it's the Fourier transform of the aperture function. And as far as I know, this may be the reason in physics why they use that particular convention for the Fourier transform. I don't know if that's true or not, but it is a reason for it. All right. So if I would have defined the Fourier transform differently, if I would have defined the Fourier transform with a plus sign here instead of a minus sign, then I would have had maybe the more elegant results saying that the strength of the field at p, the value of the field at p, is proportional to the Fourier transform. Now in the notes, actually, I fudged this. I wrote things a little bit differently, so I wound up with a Fourier transform, but that's really not true. So what I gave you here is it's only a question of differing between the plus sign and the minus sign. So I haven't had the somehow nerve to go back and change the way I wrote it in the notes because I really wanted to come out in terms of the Fourier transform, but I had to be honest. So this is our result. All right. Now it's pretty. This is a wonderful result. All right. This is a wonderful intuitive result. All right. It took us a while to get here, but what it says is that under the Fraunhofer approximation, so for far field diffraction, the strength of the field at the image plane is the Fourier transform. Think of just the Fourier transform. Is the Fourier transform of the aperture function. All right. You have an aperture plane with a bunch of slits cut into it, and you have a diffraction pattern. What do you see? You see a bunch of bands of white and black. You see light and dark. What are those bands? Analytically, they are given by the magnitude of the Fourier transform of the aperture function. All right, that's the takeaway headline. All right, for far field diffraction, the magnitude, which is what you see, or maybe let me put it this way, the intensity of the light, because that's what you're seeing, is the magnitude of the Fourier transform of the aperture function. All right, that's the summary, that's the headline. And that's a very valuable thing to know, all right, if you go into this area. If you don't go into this area, who cares? But if you go into this area, or if you want to have a conversation about it, this is very important. I was just talking with a friend of mine, Marty Fayer, who's in applied physics, just the other day, and we were talking about what I was doing in the class. And I was saying that I was going to do this, and he was very pleased to hear that, because what he finds is that students today, when they're confronted with a diffraction problem, will try to solve things numerically. They'll set up a MATLAB program and they'll do all sorts of computation. But what he really wants them to be able to say is this sentence, all right? At least as a starting point, to get some intuition for what the field should look like. Think about what the apertures will look like. You have all this experience taking Fourier transforms. That'll tell you, that'll give you a good sense of what you should be seeing on the image plane. I mean, you can do more detailed computations, numerical approximations, and so on. But starting with this as the principle of what the field should look like, what the intensity, what the light should look like that you see, is given by the Fourier transform of the aperture function. It's an extremely nice result. All right, so let's do some examples of this. All right? Let's do single slit diffraction. All right, the most basic diffraction experiment, a single slit. What is a slit? A slit of width, say, A, is given by a, and let's say just centered at the origin. All right, so this is at the origin. Then the aperture function is described by the rectangle function, pi sub a of x. That's a function which is 1 from minus a over 2 to a over 2, and it's 0 otherwise. So the aperture is pi sub a of x. That's the function that describes a single slit. All right? So what do you see on the image plane? Sorry?
Not 1 minus?
No, it's 1. The rectangle function is 1 on the aperture and 0 off the aperture. Okay? So pi is 1 when x is between minus a over 2 and a over 2, and it's 0 outside that. So what is the intensity of the light? So the light, the intensity of the light is the Fourier transform, and this is the inverse Fourier transform. This amounts to the same thing. Intensity of the light on the image plane is, what is the Fourier transform of this is, I write down here, is A sinc, let me write it down in terms of the variables, A sine theta over lambda. Writing P equals sine theta over lambda. All right? You see, oh, excuse me, I'm sorry. The Fourier transform is given by this. The intensity is the square of that. All right. Fourier transform is this. The intensity, you see essentially the magnitude of this. All right, so you see the square of this, you see the magnitude. So absolute value of this. All right, so why do you see lights, why do you see bands of light and dark? Because that's what the sinc function is like. The sinc function is big in some places and small in some other places. It even has zeros. Now, the zeros are the places where it's dark. You take the absolute value of this thing to actually see the magnitude, so you're always seeing either some light or black, all right? But you're seeing, it decays. It's bright in the middle, then it has all these, sort of little variable bands of light and dark separated by black, separated by zero intensity. And that's because it's not Fourier transform. It's given by the Fourier transform of the rectangle function. Ain't that cool? I think it's cool. All right? Now, let me take another example. Let's tie in. I said I wanted to bring in delta functions here, so let me do that now. Then I won't say too much more today. We're going to do this again next. We're going to take this up again next time a little bit even more generally when we talk about crystallography. And we'll talk about sort of one-dimensional crystals. We'll do higher dimensions a little later in the course, where I'll bring the delta function in even more definitely. Suppose I have a point source. All right? Suppose the aperture is a point source, like a pinhole, but smaller than a pinhole, a point. All right? Then what's a reasonable approximation of the aperture function? Delta. All right? Then A of x is delta of x. All right? Now, before I write down the formula, if you have a point source on an image plane, on the aperture plane, and you put an image plane far away from it, what do you expect the illumination to be on the image plane? Pardon me?
Circles.
No. A circle would be a real. I mean, what you get on the image plane of circles would be a real circular aperture, but this is a point aperture. And the image plane is far away. All right. You would expect constant. Right? You would expect a constant illumination. You would expect the illumination on the image plane. If the image plane is far away, it would just be uniformly illuminated. Uniformly eliminated. Eliminated? Did I say uniformly illuminated? All right? That is a physical interpretation of the fact that the Fourier transform of the delta function is 1. All right? This is a physical interpretation of the Fourier transform of the delta function, or the inverse Fourier transform of the delta function amounts to the same thing, is 1. All right? Because the intensity of the light you see on the image plane is the magnitude of the Fourier transform of the aperture function. The aperture function is given by a delta function. It's a point source. All right? And its Fourier transform is 1. You expect uniform illumination on the image plane. Ain't that cool? I think that's cool. I think that's cool. All right? I'll do one more example. Do it over here. The famous, one of the things that really got people freaked out was the so-called double slit experiment of Young. And I won't talk about the experiment. I won't talk about the experiment or what the results were. But that was a famous early experiment in light. So Young's double slits. You can look this up. And of course, you know, talking about diffraction, light diffracting through two slits, or talking about particles going through two slits has been a famous experiment in physics for forever. So the situation might be something like this. Might be where I have two slits that are modeled by two rectangle functions. All right. Say a distance. Say the distance between them is. I'm gonna have my. I'm going to stick with my notes here. So say the distance between them is b, and they are each of width a. All right? So it's given by, the aperture function would be given by, the sum of two rectangle functions is pi sub a of x minus b over 2, pi sub a plus pi sub a x plus b over 2. All right, so the distance is b. The distance between them, say this is at height plus b over 2. This is centered at plus b over 2. This is centered at minus b over 2. So it's easy to write down the aperture function. It's just the sum of two rectangle functions. It's 1. They don't overlap. It's 1 when you're in either aperture, and it is 0 outside it. Okay, and you're either in one aperture or the other aperture or outside it. And what is the Fourier transform? What do you get? And I think I have a picture of this. I'm sorry I didn't check. I know I have at least a graph of this thing in the notes. I don't think I have a picture of the actual diffraction experiment, but you can find it. You can track it down. So the Fourier transform of this, we know how to do this. This is the modulated version of the, or it's a shifted version of the it's the sum of two shifts of the rectangle function. And we know how to find that via the modulation theorem. In the notes, I talk about how to do this by using the delta function, actually. Or you can do it this well. I'll just write down the result because we got to go. So you get, and I'll just A sinc A times P. So P is again sine theta over lambda times cosine of 2 cosine pi BP. So again here, P is equal to sine theta over lambda. Theta is the angle that you are diffracting through at P. Okay? Then it makes it P. And that you should recognize this. This cosine factor comes in because of the modulation, because of shift plus and minus, plus b over 2 and minus b over 2. And this sinc comes in because that's the Fourier transform of the rectangle function, the stretch rectangle function. All right? In the notes I mentioned I wanted to actually use this as an application of the delta function because I wanted to write this as a convolution of two shifted deltas. But I'll do that next time, or I'll talk a little bit more generally about this next time. I just wanted to give this result too because this is another famous experiment and famous formula in physics, what the diffraction pattern for the double slit experiment is. So look that up. I'm sure you can Google this, and you'll get pictures that correspond just to this sort of function. So it's a physical, I should have said actually, this is a physical interpretation of the Fourier transform of the delta function is the constant function 1. The single slit or the sort of double slits are physical interpretations, physical manifestations of the sinc function. All right, you actually see them coming up in diffraction experiments. It's cool. All right, that'll be it for today. Then on Monday we're going to take this a step further, talk about crystallography, and that will actually lead us into a discussion of sampling. You'll see. Thank you very much.